All right, everybody shut up. All right, so let's talk about the midterm, and then we're going to start talking about threads and sockets. So all the grades should be up, I think, on the midterm. Grades were I think fine. I don't remember what the class average was. It was, I don't know, maybe an 80, something like that. A lot of A's and B's. So if you did substantially worse than that, maybe try to determine why you sucked. Was it not studying, whatever? Okay, so this first one, why does a compiler need to know about the architecture and OS it is targeting? This one was actually partially missed way more than it should have been. So obviously it needs to know about the architecture related to the assembly language it's going to output, right? Why does it need to know about the operating system? It's because it takes into consideration the system calls of the operating system. Okay, so I mean, some people would say things like, it produces a different assembly. That doesn't necessarily tell me. You probably maybe knew what you were talking about, but doesn't really tell me that connection. The reason it's producing something different is because it's taking into consideration the assembly or the system calls of the underlying operating system. So it needs to have those two things in order to create an executable for that particular OS running on that particular architecture. But
this is a strange question, but why was there like so many different architectures? Why was there one that they did like early on or like partially early on?
you mean like early on?
Yeah.
Because everything was proprietary.
Oh, okay.
Yeah. So like now we've whittled it down to, hey, this is, everybody uses Intel or AMD or Qualcomm now on mobile, where you had like Sun Microsystems for a long time was a really popular server architecture, and they had their Spark chips, which were a whole different thing. The 325 class is looking at MIPS computer architecture. The assembly language for MIPS is maybe, people say it's easier to learn. I actually think ARM is maybe easier. I don't know that MIPS is all that friendly, but the education history of it says MIPS is easy to learn. So MIPS processors actually still do exist today, but it's a lot of embedded systems like washers and dryers and stuff like that. But they existed for computing in the very early days. And then you had all sorts of different, it was common for the software makers and the hardware makers to make their own stuff. IRIX, Silicon Graphics had their own operating system and made their own hardware as well. Yeah, but now nobody uses any of that stuff. It's all, if you go up to like the mainframe level or the really giant supercomputer level, you're still probably dealing with proprietary type stuff. But at the consumer level, you've heard of all the stuff. It also made it really expensive to maintain things. So when I was at Western Illinois University, whenever we ran our whole Unix server stuff was all Sun systems. So, we had like a, I don't know, $30,000 a year just retainer with Sun Microsystems. Whenever we had a problem, like any sort of problem, they would come out with like technicians, like soldering irons and stuff like that to fix stuff. It was kind of ridiculous. Once Oracle bought them, they got rid of their computer division. It is interesting though, if you go on eBay, you can still buy Sun Spark stations for like a shocking expensive price still. Like they're surprisingly expensive given their actual capabilities. The Sun fanboys, I guess, will be like, oh, well, it's still really fast for Unix-y stuff. Well, I mean, really fast relative to what we have today is not a thing. And then their death knell, opposite from Apple, is when Sun switched to, they had an operating system called Solaris, which was a Unix operating system. And when they switched, they made Solaris run on Intel. They switched their computers to Intel, and then they just died as a hardware company on that side. Okay, question 2. Why might a process be less preferable to a thread? All right, so something along the lines of processes being heavyweight, threads being lightweight. probably the main things I'm looking for, things like processes get their own amount of time on the CPU, where threads share the CPU time with the parent process. Something along those lines. Let's see. So write some C code that creates a child process and has the parent print if they are the parent, and the child print if they're the child. I said you don't need to include libraries and stuff like that. There was actually some really interesting long-winded answers here with like loops and stuff. I don't know where those were coming from, but I mean, it would be something like if PID is equal to fork, if PID is equal to 0, F child, else F parent, something like that. Should have been enough. So how do you identify the child versus the parent after a fork system call? Yeah, so I'm not sure where the overkill came from for some of these. In fact, there was several where you like wrote loops and stuff and it never identified who the parent was. Like you did all this extra magic trick stuff and then never actually solved the problem. Difference between get PID and get PPID. Get PID gets the process ID of the current running process. PPID gets the process ID of your parent, whoever created you. Steps necessary for a process to create 3 child processes and for those children to become aware of the other children's process IDs. This one was actually missed fairly often, at least in part. You know, so your starting point is going to be something you're going to have to call fork 3 times, one way or another, right? We're going to create 3 child processes. And then how do these guys communicate with each other? I mean, there's different, some people talked about signals, some people talked about pipes. Probably the common answer would be shared memory, right? Let's create some shared memory for those child processes to share their process IDs with each other. Where the kicker comes in, and this is related to a future question there, is so if you're going to have 3 child processes, you probably need to create enough shared memory for 3 integers, right? 3 process IDs. But the question is if you're child 0, 1, or 2, where does child 0 store their process ID in shared memory? Where's child 1 store their process ID in shared memory? Where's child 2 store their process ID in shared memory? They're not just going to be overwriting each other, right? Some people did describe kind of a fairly convoluted system involving signals and shared memory, where you basically had shared memory for like a single integer, and then the children throw up signals or something like that to let them know when to look and things like this. But I mean, realistically, it was a matter of taking advantage of knowing that the original process, that if you have an integer like int pos, and you started int pos off at 0, and every single time you created a new child, you incremented that. So that child got a copy of that. So the child would put their process ID in bucket pos of that shared memory array. So the first child would put it at bucket 0, the second one would put it at bucket 1, the third one would put it at bucket 2. And then when a child goes and reads from shared memory, they know there's 3 buckets there. They would be interested in the 2 that aren't equal to their own process ID. Does that make sense? Or at least they could be just look at the 2 buckets that they weren't in charge of. So that was kind of the piece that was missed, was the piece of how do the children actually know where to put their actual process ID, not just somehow magically put it into shared memory. Shared memory is how it becomes available to all of them, but you had to have a little bit of strategy there on where to put it. Questions on that one? You could. Yeah. So you could create 3 different segment IDs, and each child, and because segment IDs are integers, all 3 of them would know about segment IDs. So then all 3 children could just attach to the 3 different segment IDs and grab process ID from there. In fact, that's probably, well, is that really any easier? Yeah, I don't know. It's not as nice algorithmically as just having a 3-bucket array, but from you're really actually still doing the same management. Which variable do I look at to get it? Which bucket do I look at to get it? Kind of the same thing. All right, difference between raise function and kill function. So this is related to signals. So raise is how a process sends a signal to itself. Kind of maybe use this for like exception handling, something like that maybe. Whereas kill has a targeted process ID you're sending a signal to. All right. This next one was commonly missed for at least some points off. So what does this code actually do? So, many people broke it down kind of relatively accurately. When we say malloc 2048, the 2048 here is 2048 bytes of memory. Malloc allocates some number of bytes. So in this case, we're allocating 2048 bytes of memory. Now, this comes out as a void pointer. So that means a pointer that does not dictate the default size of a step through memory. So when we change this to say, treat this guy as an integer pointer, int pointer stuff holds a memory address. It wouldn't matter if stuff was a void pointer or a char pointer, it still would hold a memory address. It still would hold the same memory address. That is the base address of a chunk of land. And it's fair to call that an array, but it's only an array if you actually choose to use it as an array, right? It's a chunk of land, and how you walk through that land is kind of up to you. Now, the implication of this code here is that I intend to store a bunch of integers there. So when I say store something at bucket 0 versus store something at bucket 4 is 4 integer size steps by default off the base address. Okay. So with that in mind, visually, the intention of this is to store a bunch of integers. But the follow-up question to that is, can stuff hold a string? Now, first of all, an interesting, a good follow-up question is, well, it depends. What do you mean by string? Strings do exist in C, but they're represented as character pointers, character arrays. All right, so can a string be held in here? Sure. When you have a string hello world, that's going to be stored in, well, if you have a string of hello, let's say, that's going to take a total of 6 bytes of memory, because a char is held as a ASCII character, which takes up 8 bytes. And then the \0, the string termination character, is going to be 1 last byte. So the string hello, which has 5 characters in it, is going to require 6 buckets, 6 bytes of memory. Well, I have 2048 bytes of memory here. No problem. I can store a string there easy peasy. Now, how do you get the string into memory then becomes kind of an interesting thing. I didn't necessarily expect you to know about some of the string libraries. There's a library or a function called string copy, which takes in a destination address and will copy the string there somehow. It'll get the string into memory, but nothing necessarily keeps you from doing some interesting stuff with maybe bit shifts and bitwise ands and ors and things like that to get, I mean, really, if you think an int is 4 bytes big, that means in the size it takes 4 bytes, you can actually fit 4 chars. Or the size it takes to hold 1 int, you can fit 4 chars. So if you can get those guys melded together, and where the first 8 bits is the first character, the next 8 bits is your next character, the next 8 bits is your next character. So you got to get a little creative. How do I massage my integer so that it's actually storing the ASCII value of chars? Because if I'm going to say put something at bucket 0, the thing I'm putting at bucket 0 will be 32 bits. Okay, or 4 bytes big. So you would need to make that number mean something more than just a number. You'd have to hide your chars in there. And then if you treated it like a string later on, it would read from it just fine, because memory is memory. Nothing changes with the memory by me putting int pointer in front of it, other than the default step size I use when I walk through memory. That makes sense? So I kind of accepted answers either way for can you store a string in there, depending on what your explanation was, because some people said, no, you can't store a string, but then they went into some pretty significant detail of the complications of trying to put a string in there, which do exist. But you could still get a string in there. All right, so questions about that one? What problem does a semaphore solve? A lot of people, and then I said, what does it mean when incrementing or decrementing a semaphore is atomic? So the atomic part was the part that was most missed. So semaphore, a lot of people called it the critical section problem, which is actually kind of the most correct answer. I'm not a big advocate of like vocabulary words or things like that. So as long as you kind of understand what the critical section is here's a chunk of code that I want to make sure only one or a limited number of processes have access to at an individual point in time. You use maybe my bouncer analogy or something like that, where somebody's kind of, you know, protecting access to some section. That's the problem the semaphore solves, is it makes sure that there's some level of security around a important part of the program. Now, atomic is actually the more important thing. Some people, then this is related to the atomic. Some people also referenced it also solves the race condition problem, which is also a true statement. When two processes arrive at the same resource at, let's call it, roughly the same time, and you know, when we're dealing with this stuff at computer speed, roughly the same time, we could be measuring in, you know, nanoseconds, right? And at that point, it does matter what the reflexes of that bouncer, what those reflexes are like. And that's where it's important that the way a semaphore is incremented or decremented, it operates as an integer, but how fast it increments or how fast it decrements, we can think of it as kind of being that bouncer's reaction time. And by saying it's an atomic operation means it happens as if it occurred in one CPU cycle. Whether it actually took a single CPU cycle or not, at the architecture level, it happened as if it was in one CPU cycle. That could be managed by the operating system, or it could be managed by the processor. Most of our modern processors have the ability to, at the hardware level, have atomic operations. But otherwise, there would have been some interesting stuff they would have done at the software level just to make sure that certain things just weren't possible. So really, atomic operation means it happens as if it's in a single CPU cycle, which means that you cannot have both, if we're dealing with only two processes, both of them grab the same resource at the same time, because they weren't able to get there was no delay. If it happened in two CPU cycles, let's say, technically, if the moons aligned, both of them could have gotten access to it if one of them snuck in right between the two CPU cycles, something like that. So atomic is an important aspect of semaphore. Otherwise, semaphore is just for show. You can just use a normal integer to, if it's not atomic, you can just use a normal integer instead of a semaphore to protect it and hope for the best. All right, questions on that one? Convert 13AB from base 14 to base 3. I think most people got this one right. So I think the couple people that messed this up tried to do the hexadecimal to binary trick, thinking that that was going to work. So if we say, because 13AB could be a hexadecimal value, right? The only reason you know it's not a hexadecimal value is because I told you it's a base 14 value. So if this was a base 16 value, you could give me the binary version of each of those hextets and have the correct binary version, and then maybe go from there to get it into base 3, although the people who messed this up just left it in binary. Look, you asked for 14 to 3, I gave you 16 to 2, deal. so understand that those shortcuts, the hexadecimal to binary and the octal to binary, the only reason those shortcuts work is because for hexadecimal, you can describe the entire hextet library, 0 through 9, A through F, 0 through 15, using 4 bits in its entirety, no wasted bits. You have exactly 16 permutations of 4 zeros or 4 zeros and 1s to get all of those hextets. And the same thing is true with octal, except you could do it in 3 bits. There's 8 unique permutations. All right, so that's why those shortcuts exist. In this case, you were not able to use the shortcut. Instead, what you'd have to do is you would convert from base 14 to base 10 first. So if I just write this out a little bit, this was a 10 and this is an 11. So this is 0, 1, 2, 3. This is 14 to the 3rd power, 14 to the 2nd power, 14 to the 1st, 14 to the 0th. Spread these out. What's 14 to the 3rd power? 2744. 14 squared is 196. This is 14. This is 1. So we had 1 times 11 plus 14 times 10 plus 196 times 3 plus 2744 times 1. And that's 3483. So that's your decimal version of that. So that's one pattern of going from a base to decimal. Then your secondary pattern is how do I go from decimal to a base? And that's where you divide this guy by 3 over and over and over again, recording the remainder. 3483 divided by 3 is 1161. Remainder 0. $1161 divided by 3 is 387. Remainder 0. 387 divided by 3 is 129. Do we really not have remainders yet?
It's a lot.
129. 129 divided by 3 is 43. Remainder 0. $43 divided by 3 is 14. Remainder 1. All right. $14 divided by 3 is 4. Remainder 2. 4 divided by 3 is 1. Remainder 1. 1 divided by 3 is 0, remainder 1. Then you read your answer from bottom up. So this is 1, 1, 2, 1, 0, 0, 0, 0. Is the base 3 version of the base 14 number 13AB. Make sense? Like I said, that most people got that one right, so that's good. Over the years, you've learned both patterns, and so the one confusion was that shortcut only works sometimes. You can't just say, "Oh, I see A's and B's. Let's just do the shortcut." That's not going to fly. It'll work for base 4, 8, 16, and 32. You need 5 bits for 32. 6 bits for 64, yada yada. So you can keep going after that. You run out of letters. Yeah, go ahead. Base 3 and base 9. Well, no, because you don't have you'll have wasted bits. So to represent all the base 3 numbers, so all the base 3 numbers are 0, 1, and 2, right? So let's see, 0, 1, and 2 takes up. So that's 0, 0, 0, 0, 1, 1, 1. You can do all of base 3 in 2 bits. Base 9, 1, 1, 1, 4, 5, 6, 7. You can't do 9. 9 takes 4 bits. Yeah.
Is there some kind of relation like that with other bases?
No, and the reason is it's not that there's something super special about. You might say it's the reason why binary is our base of choice for computers, but that's also, it's almost like moons aligning type thing. It's also the rationale for, like, digital dictates zeros or ones, right? On, off, that kind of sort of makes sense that we have to do everything with switches. But at the same time, it's the fact that I call them bit spaces. You have some number of bits in a row. If you can represent something else by fully using a bit space in its entirety, no more, no less, then there's likely a compatibility there, or either a mathematical compatibility or a compatibility that you can build in. Because you effectively, if you could say, hey, I have something that in, so what, 6 bits is 64 different unique possibilities that you can do 6 bits in. So if you have 64 unique outcomes, you can represent all those 64 unique outcomes using exactly 6 bits. How you do, I mean, with these things, we're actually doing the math with those 6 bits, right? We're converting the binary to decimal and say, oh, well, this is a 10, this is a 12, this is a 3. But I mean, you can represent the entire Unicode character set using bits as well. And you can fully deal with Unicode, the 16-bit version of Unicode. Now Unicode's got multiple big brothers because we decided, oh, well, you didn't cover all the languages and we need to be inclusive. So, and then we have symbols and stuff like that that were left out of the original Unicode as well. But mathematically, the pattern works for our bases of, technically it will work for base 2, but you're already in base 2. So base 2 for 8, 16, 32, any power of 2. It would work for. All right. And then the other thing I'll throw back in there, in case this was part of the confusion of the question, make sure when you see a value, you do look to see what base it was advertised in, because this is a legal base 16 number. It's also a legal base 15 number and a base 14 number and a base 13 number and a base 12 number. It's not a legal base 11 number. We don't have enough bits for a B wouldn't be legal for base 11. But just looking at the number does not give you enough information about what base it is in. You need to be told the base. Make sense? So it's unclear to me whether you thought the shortcut just always worked when you have A's and B's and stuff, or if you assumed that was a base 16 number and you knew the shortcut worked. Okay, and then what problem does shared memory solve? So something along the lines of, you know, the overarching thing we've been talking about with inter-process communication, memory that lives at the operating system level, global memory outside of protected memory of an individual process, something along those lines. All right, questions about any of the exam questions? And points were lost just on those like three or four questions that I mentioned, and very few questions were like zeros. It was usually like half credit or like an 8 out of 10 if you kind of drop the ball on a little part of it or something like that. All right. Let's see, this is. All right, now I don't know if this is good news or bad news, but at least for a little bit here, we're actually going to switch over to Java. Is that good news or bad news? Yeah, I want to answer. What's the perception of the audience? Is it good news that we're switching to Java from C?
I think we're gonna do less debugging.
Well, that might be true, but we're doing it because we're looking at network programming. But we probably will be, we'll probably always have more recent documentation. That's probably a fair statement. Right. But this is going to be, I think, interesting. Well, I mean, the short answer is there's no reason why you can't, but in order to test some of our stuff. So let me kind of give you an idea of like where we're going with this over the next little bit. And and understand, it's not like I have this weird love affair with online GDB. It's just a low maintenance situation where I don't have to worry about some student coming up and saying, oh, NetBeans isn't working for me, I'm getting this error, and Eclipse isn't working for me, I'm getting this error, and I'm using some other weird third-party open source gives food for corn crops in Africa project or something like that. Like, all those things are great, but I can't manage 50 different installs of 50 different pieces of software. But the limitations of online GDB have been somewhat, let's say, frustrating. But the bigger thing is when we get into the network stuff here, we're actually going to have multiple applications running at once that are going to be talking to each other. We're actually going to create those multiple processes that will be talking to each other. They will exist as separate physical processes. We start this Java program, we start this Java program, and we're going to have a way of getting to the other one. And part of that is going to deal with either IP address or via localhost. And I am pre-predicting, it's a double prediction that online GDB is going to have significant security stuff in place for IP addresses. So I think it makes a lot more sense for us to, there's no reason why you can't write either of the pieces on online GDB. But when you actually go to run it, I think you're gonna have to run it external to that. Otherwise you won't be able to talk to the two sides. Okay. So let's talk about threads for a little bit, because they were trying to transition from processes to threads. Threads are, we can say, in almost every way better than threads, especially with modern operating systems where threads can actually be scheduled on separate CPU cores. So now you don't actually have the real limitation of well, I'm actually sharing all of my CPU time as a parent with my threads. If there's an open core on the CPU and the thread is able to run, the operating system will schedule it, even if he's not entitled, the thread's not entitled to that CPU time. If nobody else is using it, the operating system's job is to make the CPU as busy as possible. Okay. So when we talk about threads, we're talking about lightweight processes. So lightweight process that shares, let's just say, a lot with its parent. The operating system will kind of dictate at what level does the sharing absolutely cut off versus what can the operating system kind of reach in and make a game time decision to give you more CPU time or something like that. But from our expectation as a programmer, we are solving the blocking problem, right? Because in all of our cases, when we create a second process or a second thread, the first thing that we're gaining is blocking. We are able to have two things occur as if they're both happening at the same time, or at least keeping us from having one line of code preventing the rest of the stuff happening in case that one line of code is going to take time. Okay, so threads and processes both solve this this problem. So how do threads communicate? So let me, shared memory, like we just talked about. When we have multiple processes, each one of those processes lives in its own little world. And shared memory gives you a plot of land that is outside of that world so that processes can communicate with each other through that plot of land. We also have some other tools that processes can use, can communicate with each other. Kind of like walkie-talkie type things or whatever. Now, with threads, if you have a single process that spawns off 3 threads, all of those threads actually have access to the same memory space. So you no longer need something like shared memory. So if we draw a picture of what that looks like, if we have P1, P2, P3, and we're dealing with multiple processes, each one of these guys has its own little protective bubble that it lives within. And this bubble has its own memory space. And then what we end up having is an operating system level bubble. And this is where shared memory would live. So shared memory would live in that green section there to allow those two guys to talk to each other. If we're dealing with a multi-threaded model, and I'll create a T3 just for our example here. Well, actually, there's only 3 processes there. We have 3 total things here. the original process and the two threads that it spawned all share that same memory space. They don't need to go outside. There's nothing that prevents them from using shared memory. They can just say, hey, whatever, I'm going to store stuff in shared memory. So in case at some point I flip over to multiple processes, or maybe you have some sort of weird example where within a single program, you are having multiple processes as well as multiple threads, or like in our example here, we're going to ultimately we're going to write a chat server where we're going to have a piece of server software running using sockets, and we're going to have a bunch of clients. Everybody who wants to chat is going to be running a client application, and those are separate processes. By internet standards, these are probably separate processes running on completely separate computers, right? So in that case, shared memory likely does not make sense. But if it just so happened that we were all sitting on the same computer, multi-user computers that run Linux, we could all telnet into the same core computer, log in with our accounts, and there could be a server running on port 300 on there, and we could each connect our client or chat client to it. And technically, since all of our processes are running on the same operating system, our clients could communicate through shared memory if that was something that made sense. But when you typically think about the internet, now we're going even beyond that. So, when we think about the internet, what lives at the next level up this is like the cloud, right? Lives outside of the actual computer you're on, but maybe allows things to be shared among multiple resources. All right, we actually have left the computer. Okay, so we're still dealing with inter-process communication at this point, just across multiple computers. All right, so when we're dealing with multi-threaded, we don't have to worry about leaving this local ecosystem and using shared memory, although nothing prevents us from doing that. All right, questions on kind of that picture version of processes versus threads? So now we want to think about pipes versus something called sockets. All right, so we looked at pipes a little bit. We didn't go too much into them because we're going to be looking at sockets, and they are very, very, very similar to each other. Pipes are unidirectional. So they can only communicate in a single direction. And live locally on an OS. Sockets are bidirectional. Can communicate in both ways and can live on a single OS, but are not limited to this. All right, so we could really think about sockets as being like, upgrades to pipes. Like, it's not an unreasonable thing to think of sockets that way. You can certainly look at some performance things, and maybe pipes outperform sockets in many ways for certain applications, because pipes are a primitive type at the operating system, where sockets are kind of having to bridge a much bigger world given their capabilities. So you might be unnecessarily going through multiple layers of stuff with sockets, but it gives you that additional flexibility. And we could just say, hey, computers are really fast, so who cares? Something like that. Okay. How do we uniquely identify a running process? All right, so up to this point, when we've thought about processes, because everything's, whenever you have a program, there's going to be at least one process involved, right? Even in this picture, whether we had multiple processes here or multi-thread, we still had a process involved. It's always going to be that top level process. And a lot of modern applications, what it does is it actually takes that top level process and keeps that as lightweight as it can. And then it spins up a single thread of execution. So you have a default thread that runs inside of a process. And then that thread ends up being the parent thread of any subthreads it creates. I'm not sure that makes a significant difference for us. It's more of a security thing where processes do not expose very much to other processes unless they choose to through things like shared memory. But anyway, you cut it, anytime you run an application, a process will exist. And up to this point, we can uniquely identify a running process by its process ID, right? So this is a unique int that identifies a running process on a computer. Okay. Say single OS. Now, what if I have a process that lives on a different computer? So I want to, I launched my chat server here, okay? And Emily connects to the chat server with her chat client program. And so she wants to talk to the program that's running on my computer. Now, let's assume she had the process ID. Let's say it's 6722 is my process ID. Does that do her any good? Knowing what the process ID of my computer program is on my computer, on my operating system? Because she can certainly have a process ID 6022, whatever I said, on her computer. That's a whole different process, right? So process IDs are only good if you want to talk between processes that are running on the same operating system. That process ID is meaningless to her. So how does she uniquely identify my running process on my computer? How do we make that jump? Go ahead.
It can be similar to how we had like that issue type of thing.
Very little sense. Tell me more.
When we were trying to do things with shared memory, both processes printed out the identical memory address when they weren't before we weren't shared memory. But that still wasn't the case. Is there something similar there? Am I getting closer?
No, I kind of still don't know what you're even saying. Well, maybe it'll be easier to think about, like, I mean, right now we happen to be sitting in the same room, so, she could wad up a piece of paper and throw it at me, but we still are sitting on different computers, right? So this process ID on here is completely useless to her, other than her only evidence that I'm running the process that she cares about is that I've told her, okay, I've launched the chat server, okay, something like that. Okay, so now I want her to somehow be able to find that program. Go ahead.
I was gonna say, would it be possible, like if both of your computers have two different processes, could you have like a separate process ID that both of the process IDs pinpoint to in order to have a direct communication?
Okay, so maybe a shared process ID,
Yeah.
shared in the cloud?
Yeah.
Okay. Okay, so if we have multiple computers, multiple OSs, where we have two programs that need to talk to each other between those computers. How do we uniquely identify those processes? And this actually becomes kind of an interesting thing. I think both of you sort of said the same thing, but there's actually multiple implementations of this. For a long time, there's been this idea of a distributed operating system. We're not going to go too far into that because that's more of a operating system core subject, but we can talk about the challenges with it from a programming perspective. Although, did you talk about distributed OSs in 350?
I want to say
Okay.
It was like one of those like talked about it, but.
Okay. Well, so we could talk about it a little bit because this is kind of like OS2 this class, but we focus more on the programming. So if we had this global, so right now I've already labeled something here called the cloud. And the cloud, it's just this ubiquitous name that we have for storage and stuff that's outside of this computer. It's up there somehow, right? And now that idea of storage has gone a little bit bigger. So now we have compute power, right? Some people, they would have maybe a low powered computer, or from a supercomputer perspective, a relatively low powered computer, and they want to leverage the Amazon's 4 zillion computers to do a whole bunch of number crunching. So they're going to leverage the resources of this global monster computer that has zillions of processors, a bunch of RAM, a bunch of storage, all these things. So when you really think about the animal that is the cloud, it sort of kind of is this like giant computer in the sky. Does that make sense? And we're having our local computers do some stuff locally and do other things using those remote resources. Now, what we don't have right now, we have kind of micro versions of it. If we think about something like a distributed operating system, way back where we talked about what are the different things an operating system provides, right? Provides process management, provides CPU management, memory management, all sorts of stuff like that. So if those are the things that a operating system provides, do we actually have the idea of an operating system in the cloud that we use to accomplish this cloud computing stuff? Is like Amazon Web Services, is AWS, is that effectively, if you squint, a distributed operating system? You have to use Amazon's tools if you do AWS. We'll just say tools, see what it gives us. Yeah, here's just kind of an example over here of these featured services, but they have a zillion other things other than that. But here's by use cases. So we have archiving, backup and restore. They have blockchain services, cloud operations, shared containers, database stuff, yada yada, DevOps. So you can have your whole development cycle all up in the cloud. Really that starts sounding a lot like the features of an operating system. These are things that live in the cloud. So rather than using our local operating system for this, we're using it in the cloud. We have to play by AWS's rules, whatever their security stuff is, whatever they lock down, whatever they don't lock down. AWS typically does something called IaaS, infrastructure as a service. So rather than giving you this kind of turnkey solution where you can just, you go in and you do what you're going to do, it kind of gives you compute resources that are more generic. Like you can get your own Linux box that lives in the cloud from AWS, and you can do whatever you want with that. And it's going to be a very elastic type of performance thing where you can have more or less memory on demand, more or less computation power on demand, things like that. But you then also are now responsible for solving some of those harder problems of maybe your front end and stuff like that. where if you look at like Google Firebase or Microsoft Azure, you know, those guys are platforms as a service. Azure's sort of kind of a hybrid-y thing like that, but I'd call it a platform as a service, where you effectively have to do things the Azure way, or you do things the Google way with Firebase. But what that comes with, similar to us saying you're doing things the Mac OS way, or you do things the Windows way. What that then comes with is you have effectively a single point of entry into the cloud. And through that point of entry, you can launch services, launch applications, or it has stuff running in the background that manages these things for you. So we end up with this idea of something that at least starts to think about the idea of a distributed operating system. So a distributed operating system would solve all of the normal OS problems, but at a global level. Okay, so it solves the normal OS problems at a global level. And the users might be child OSs. So for instance, maybe Windows, Mac OS, Linux. So we kind of plug into a more global, we have our local little world, you plug into this more global world. Almost Chromebooks are like based on this idea, right? So when you get a Chromebook like they have in like elementary schools and stuff like that, you effectively have a lightweight computer that runs a web browser, and you're reliant on everything being external. You know, everything living up in the cloud, all the services and stuff provided to you being in the cloud. Now, typically, so when you first come to campus, I think the university officially says that Chromebooks are not what you want to bring to college. Now, what becomes kind of interesting with this from our perspective, especially, I know how much all of you love online GDB, and I was using that as a single example. I would have historically said that, oh, well, you know, something like a Chromebook won't work if you're a software developer. You don't have access to the tools that you historically would use. You don't have your IDEs and all this stuff. But haven't we seen that more and more stuff is getting moved away from our local computer and into the cloud? I mean, you know, you think about like what Apple is doing with like the iPad Pro, for example, and what Microsoft is trying to accomplish with like their Surface. So the Microsoft Surface started off as a laptop that acts more like a tablet. The iPad Pro starts off as a tablet that's trying to act more like a laptop. And then you kind of see, well, where are the limitations of this? That what are my use cases that this guy won't let me pull off? And those use cases become smaller and smaller and smaller. Is it unfathomable to think that at some point soon, maybe there's even, I haven't looked in a while, maybe there's an iPad Pro application that is equivalent to like the Eclipse IDE. That might exist. There's no reason why that can't exist. They definitely have a Swift playground type thing, but Swift is a dumb programming language. But whatever, it's Apple's things. They can do whatever they want. But that idea of what is a use case for that keeps getting more and more blurred, especially when we start thinking about our smartphones as like productivity devices. So if we had this discussion 10 years ago talking about distributed operating systems, we would have said, oh, this probably doesn't work. And it's because distributed operating systems really has two separate things in mind. So if we are thinking about a bunch of child OSs versus dumb terminals, and we can think of this maybe like a Chromebook. I don't want to speak like a Chromebook has zero computational capabilities, but it's low. So we're going to call that's a personal only resource. Okay. But when you talk about your actual computers, you know, some of you have gaming computers, or your laptops might be very capable laptops and things like that. At any point in time, are you using all of your computer's resources? How many of you would be willing to let other people use your computer's resources? If it was secure, if they couldn't get to your stuff. Let's just make that a starting assumption. Nobody? Why not? Fine, it's your computer, but you're not using the resources right now. Oh, okay, so you're willing as long as there's something in it for you. It's not, so as long as you're secure, it's not that you're unwilling to let them use the resources. It's got to be worth your while. You're not going to foot the power bill for them. Okay, what if it was just break even? Like, it's not going to cost you anything, but you're adding to the global compute power, the global memory storage, the global whatever. You're adding to it by you being connected to that with your computer. Is that something you're willing to do as just a global technology citizen, as long as it's not actually costing you money? Or do you need to make a buck? But you want to make a buck. Never hurts. Go ahead.
For me, it would depend if it was like for family, like if I had a household or something like that, then maybe I would let that.
Yeah, we share with family and we don't ask for the payback, whatever, you get your yearly Thanksgiving dinner or something out of it. But yeah, I get that. I'm talking about completely anonymous, yada, yada, yada. Well, it is. So he's asking, is this kind of like blockchain based mining, like Bitcoin mining or Ethereum mining, something like that? Except that's really what he wants, is he wants to make something out of it. He wants the buck, right? Very greedy. It's not very becoming. It's off-putting. So, but effectively you're saying, I'm going to use some of my computational resources when I'm sleeping or something like that, when I'm not using my computer to work on some other problem, some global problem. So it's related. Yeah.
It would be something that, like, if you wanted to run, like, let's say if you do like 10 different OSs at one time, would you still be able to do that with your like processor taken up by it?
Well, that's true. So, and that's kind of where the idea of a distributed OS comes in, where, so your concern would be, okay, well, as long as I'm not actually using it or needing it, I'm willing to maybe play the game. I don't want to pay for somebody else to use it, but as long as it's not costing me anything, I'll contribute. But hey, if I want to launch a second operating system, I don't want to have my own personal computer tell me, I'm sorry that you don't have enough available RAM because grandma in Kentucky's watching Netflix, something like that. Go ahead.
Sounds like if I were in a computer to run multiple operating systems, you would have CPUs or GPUs.
But we have. I mean, all our computers have multiple CPUs. How many CPUs are in your computer?
More than one physical.
Well, yeah, right. But you have, you're running an i5 or i7? i7. So you probably have at least a quad core. And then each one of those has multiple logic cores. Okay. So the point is that you do have multiple processors. You probably have what, 16 gigs of RAM? Something like that. So right now, if you were to look at your task manager, you are probably using 5% of your computer's resources sitting here in class, unless you have a Minecraft game flying right now or something.
I'm looking at my task manager.
Yeah. So, I mean, most of your computer is being unused right now. So you have, even if you left a little buffer, you have 90% of your resources that you could give away or sell to the highest bidder. And you're contributing to the global whatever. But to Emily's point, if we had a distributed operating system, some governing software that decided how do you manage those resources, if somebody's currently using some of the resources on my computer that I need, I get priority to my own resources. So those things get shifted over to another resource pool someplace else so that I can use my local resources. And as long as I'm oblivious to that, as long as it feels like it's my computer 100% of the time and it's not costing me extra money, we'd be willing to play. There's a whole lot of ifs in there, but I mean, it's a good point. We don't want to give up a resource and then not have it. You lend your car to somebody, and then all of a sudden you need the car. Like, okay, well, now I need the car. But I would say not bad, as long as you had good, heat control. In fact, in some ways, it may actually be better for a computer. The physical computer, it might be better for it to have something to do all the time. Trying to think, it's weird anymore because like wear and tear on transistors used to be a thing, and I don't think it really is anymore. So that might actually be an aged answer. But at the very least, I think your first question was, would it be bad? I don't think it would be bad.
The heat would be bad.
If you have too much heat, you can do damage to the stuff. And if you have like a mechanical hard drive, now you got so many cycles. Our modern solid state drives do have a number of read and writes that it will support. It's much longer life than a mechanical hard drive, but it's not infinite. So there would be maybe some concern about other people using parts of our hard drive for storage, because you know that's why when you go out and you're looking at like storage for like servers, you're paying more for those kind of hard drives because they're designed with a material that has longer lasting, is made for more simultaneous reads and writes. So maybe that's not the best use case, but certainly your RAM and your CPU power would be fair game, and even offshooting stuff onto the GPU for floating point math and stuff. Like when he mentioned mining for blockchain, that's all CPU. Or, I'm sorry, all GPU anymore. In the early days, it was CPU. But now, I mean, you're wasting your time to do it with CPUs. Yeah.
First, I feel like if you like if I were to take my computer and share it with a bunch of people, I could just instantly hook up a backup station with multiple hard drives and then just allocate to those hard drives if one fails, or allocate to one hard drive if one fails, I have backup for another.
Yeah, but so as a group, we've decided that as long as it's not going to cost us anything, we'd be okay with this. Okay. So what we'll start next time is we want to talk more about this idea of a distributed operating system and where the limitations used to be and why are those less of a limitation today. Will this ever work? But then we still want to circle back to how do we uniquely identify a computer on the internet, even if we say that, hey, a distributed operating system sort of kind of exists on the internet already. Make some sense? Questions, comments, concerns, bribes? So if you are interested, we will be doing some Java stuff probably for at least the next 4 weeks. I'll probably be doing a lot of stuff from just a terminal on here, and then running two things on the terminal. If you want to do that through Eclipse or something, you can, or if you just want to get the Java software development kit installed in your machine so you can do something similar, that's fine. I'll probably be compiling them by hand, so it's easier to launch two applications at once, because Eclipse will have the same problem. How do I hit play twice? Something like that. Okay, I'll see everybody on Thursday.